In this video we're looking at number 3 from the 2019 AP Calculus test, form AB. So we've got a part of a function that is defined on the closed interval from -6 to 5. We see this part from -2 to 5. We know that the integral over that area is equal to 7 in part A here. Right, so we know that this part is a quarter circle, these two parts are straight lines, and that quarter circle has a center of 5 and 3, 5, 3, that part right there. And so we know the radius is equal to 3. This is a simple quarter circle, and we know that this point here at x equals 3, y is equal to 3 minus root 5. That'll be important for one of our questions. And so we want to find the integral. Given that the whole integral area under the curve is equal to 7, we want to find the integral of the missing part. And so we're going to just add the parts that we know to the parts that we don't know. And that's going to equal 7. And so 7 is equal to the parts that we don't know, or the integral of f of x from -6 to -2. And that will be added to the parts that we know. So we're going to split this up into two straight lines and a quarter circle. So we'll get the integral from -2 to 0. And what's our slope here? -x. And then our y-intercept is -1, -x minus 1 dx. And we're going to add to that, put it over here. To add to that, our slope is 2, our y-intercept is still -1, so we'll go from 0 to 2 of 2x minus 1 dx. And then we'll add to that, and for right now I'm just going to say from 2 to 5, and call that f of x dx. And I'll show why in a moment. So let's first work on this. It's a simple integral. We're going to split that up into parts from -2 to 0 of -x dx, and then we'll add to that the integral from -2 to 0 of -1 dx, and it's pretty easy going here. So our first part is -x squared over 2, and we're going to add to that -x. We'll take that from -2 to 0. Pretty straightforward. 0 squared is 0, 0 minus 0 is 0, and so we've got 0. -2 squared is 4, 4 divided by 2 is 2, so -2 minus a -2 is 0, so 0 minus 0 equals 0. Our next part here, so this one is 0. Our next part here, integral from 0 to 2 of 2x minus 1 dx. Same thing, we're going to split that up into parts, and we end up getting any derivative of 2x, of course, is x squared, and any derivative of -1 is -x. We're going to take that from 0 to 2. So 2 squared is 4, 4 minus 2 is 2, and 0 squared is 0, 0 minus 0 is 0, so we get 2. So this part is 2. And finally, we've got a quarter circle. Here we know our radius is 3, so the area of this circle is equal to 2 pi r squared, or 9 pi, right? But we have a quarter circle, and so the area of that quarter circle is 9 pi over 4. And we can find the area under the curve here simply by taking the area of this box, this square, which is 3 by 3, and we'll subtract from that the area of that quarter circle, so 9 minus 9 pi over 4. That's our third part. And so 7 is equal to 0 plus 2 plus 9 pi, 9 minus 9 pi over 4. This 9 should be outside of our numerator here. And so we're going to take 11 minus 9 pi over 4. We're going to subtract that from 7. And so we get our value here is equal to 11 from 7 is -4. This sign is going to change, so we're going to get 9 pi over 4 minus 4 is our value there. Pretty simple. Clean this up. Right, in part B, they ask us to evaluate the integral from 3 to 5 of 2f prime of x plus 4 dx. Well, the antiderivative of any derivative is equal to the function itself, so we don't have to worry about doing anything there, except we're going to split this up. We're going to call this the integral from 3 to 5 of 2f prime of x dx, and we're going to add to that the antiderivative or integral from 3 to 5 of 4 dx. The antiderivative of any constant is just that constant times x. The antiderivative of any derivative is just the function itself, so we end up getting 2 times f of x plus 4x over 3 to 5. Again, we're looking for this area here. Okay, so 2 times f of x, we're going to substitute 5 for x, we get 0, f of 5 is 0, and then we're going to subtract from that f of 3, we know f of 3 is this given value here, 3 minus root 5, and so 0 minus 3 minus root 5 is negative 3 plus root 5, we're going to multiply that by 2, and we get 6 minus 2, sorry, negative 6, plus 2 root 5, and we're going to add to that 4x, if x equals 5 we get 20, if x equals 3 we get 12, 20 minus 12 is 8, and so you can simplify this and get 2 plus 2 root 5 for our second answer. Next one. The function g is given by g of x equals the integral from negative 2 to x f of t dt. Now this is just kind of confusing language. We're still talking about the same function here, but we're saying that g of x now is equal to, well, if we're moving from the left to the right, we'll say from negative 2. If we stopped here, then g of x is equal to that part of the curve, the area of the underneath the curve there. And if we went to here, then it's equal to this area under the curve. And if we went over to this area, then we're going to take this part, subtract that from this part. So we're just moving from left to right and using x as the top limit of our integral there. I'll show you. So we want to find the absolute maximum value of g on the interval negative 2 is less than or equal to x is less than or equal to 5. So the first thing we need to do here is establish that g of x is equal to the antiderivative of f of t. F of t, remember, is still just this function here. So we're going to say that g of x is equal to the antiderivative of g primed of x because the antiderivative of any derivative is equal to the function itself. And so if g primed of x equals f of t, then we can just look at where g primed of x is equal to 0. When that's where we're going to find our maxima there. So for the first maxima, again we've got x and g of x. Our first maxima, our first possible maxima is we got negative 1 there. So we're going to find the antiderivative at negative 1. So if our function here is from negative 2 to x, we're just going to substitute negative 1 for x. And we're looking at f of t is our function here. So we've got negative t minus 1 dt. And this is exactly what we did in the previous example. So we end up with negative t squared over 2 minus t from negative 2 to negative 1. And we can take that out. We get 1/2 is our answer. Okay, the next one is right here. So we're at x is equal to 1/2. And we can take the antiderivative from negative 2 to 1/2. We see that we have 2 line segments, and so we need to take the antiderivative of that first part from negative 2 to 0 of negative t minus 1 dt. And we're going to add to that the second part here, which is the antiderivative from 0 to 1/2 of this new function, which is 2t minus 1 dt. And so we end up getting, again, t squared over 2 minus t from 0 to 2. That equals 0. And then we've got, adding to that, plus, say, t squared minus t from 0 to 1/2. Pretty sloppy, sorry. And so let's evaluate this function. T squared is 1/2 squared. 1/2 squared is 1/4. 1/4 minus 1/2 is negative 1/4. And then if we get 0, then we just subtract from that 0. And so our answer here is negative 1/4. Final part of our graph here is the area under the semicircle, the area under the quarter circle. And so we're going to just add to negative 1/4. We'll take the antiderivative from 0 to 2, 2t minus 1 dt. Remember that our sum of this part here and this part here is equal to 0, so you don't have to worry about that part of the graph anymore. And so we're looking for the area under this segment, which is this part here, from 0 to 2. We're going to add to that the area under this quarter circle here. And so we're going to take the antiderivative from 0 to 2 of this line segment, and we're going to add to that the area under this part, which we've already found, remember, in the previous example. We just took the area of the circle, subtracted that from the area of this box here, and got 9 minus 9 pi over 4. And so let's find this. We get t squared minus t from 0 to 2. So t squared is 4. 4 minus 2 is 2. And we're going to subtract from that t squared at t equals 0, and t at t equals 0 is equal to 0, so 2 minus 0 is 2. And so adding all of this together, remember this part here is 9 minus 9 pi over 4, 2 plus 9 minus 9 pi over 4 for our third part here is 11 minus 9 pi over 4. And then this looks to be the maximum. Okay, on to our last part. We've got a difference quotient. We just have to evaluate that difference quotient. It's pretty simple. They've already given us the basic values here. So we've got 10 to the x. As x approaches 1, this is going to be equal to 10 to the first, which equals 10. We're going to multiply that by 3 times f primed of x. Well, first let's figure out what's f primed of x. F primed of x is equal to, well, at 1, so that's this part, this line segment. So we've got d dx of the function 2x minus 1. And this is pretty simple. The derivative of any constant is 0, and so the derivative of any first order variable here is just going to be the constant coefficient there. So our f prime of x is equal to 2, and so we're going to take 3 times 2, and that all goes over f of x. F of x at 1 is equal to 1. And then we've got arctan x. Well, let's look at what's arctangent. So we've got our unit circle here. Remember, tangent is equal to the opposite over the adjacent. Well, if the arctangent of 1 means that the opposite over the adjacent is 1 to 1, that means we have a 45-degree angle here. 45-degree angle on our unit circle. If this is pi over 2, Then our 45-degree angle here, that's 0, is equal to pi over 4. So arctangent of 1, which is again opposite over adjacent, right, is equal to pi over 4. So we'll subtract from that pi over 4 and simplify a little bit. 10 to the first is 10 minus 6 is 4 over 1 minus pi over 4. Good enough. And so looking back at our answers in C, we had 11, we had 5, and 11 minus 9 pi over 4. Right, and for part B, we had 2 plus 2 root 5, and for part A, we had 9 pi over 4 minus 4.